Hi guys, welcome to lesson 4.9. We're going to be splitting this one up into two parts like we did with 4.8. We're going to talk about these things called related rates. They're a very common word problem type of question that is asked on the exam. So let's take a look at it. So first of all, we're going to talk about what a related rate question even is, and then we'll talk about how to solve two specific types. Ones that pertain to area and volume, and ones that pertain to the sides of right triangles. And then on the next day, we're just going to continue just looking at more types of problems that are commonly asked regarding related rates. So we're going to have to review a couple topics, though, before we get started. So let's remember how to do implicit differentiation. So whenever you're doing implicit differentiation, anytime this variable here does not match the variable of the term that you're finding the derivative of, you have to include a prime factor next to it. So for instance, since the t doesn't match the x, when I take the derivative of this, I'm still going to put 2x like usual, but we're also going to want to put x prime next to it. Okay? Same thing here. The t doesn't match the y, so when I take the derivative of that y, I'm going to put 2y, but we want to put a y prime next to it. And then, of course, anytime you take the derivative of a constant, you get this. Now, another thing I want to draw your guys' attention to is that what this really means right here is this means the derivative of x with respect to t. And so we could also write it like this. And today, this is how we'll be writing our derivatives, as these little fractions. And the reason for that is because this way of writing the derivative is a little bit more friendly for doing these types of problems. So that's implicit differentiation. So when it comes to implicit differentiation, anytime this variable on the bottom, which is the variable that you're finding the derivative with respect to, doesn't match the variables here, you take the derivative like normal, but you put a derivative next to it, and we're going to write our derivatives like that today. Okay? And this variable is the one that goes on the top. This variable is the one that goes on the bottom. All right? So that's implicit differentiation. That's a skill that you're going to want to be reminded of in order to do today's lesson. Let's talk about what these things mean. So, I mean, the way that we say this is the derivative of s with respect to t. But what it really means is how much s changes as t changes. That's what a slope is. You guys remember that a derivative comes from taking the limit of a difference quotient. Right? That's what we've been talking about mostly in Unit 4 at the beginning here so far anyway, right? So a derivative is the limit of a difference quotient. And what is a difference quotient? Well, it just tells you how much, I guess I could use variables that match the ones we're working with. Instead of y and x, I could use s and t. And basically, if you subtract your two s values, that tells you how much s changes. And if you subtract your two t values, that's how much t changes. So the derivative of s with respect to t is how much s is changing over how much t is changing. And the only difference between this expression and this one is that this tells us how much s is changing with respect to t at a specific point, whereas this one tells us without the limit. This one tells us just how much s changed over how much t changed on a specific interval. Average versus instantaneous, right? But basically, ds dt just is telling us how much s is changing as t is changing. So in a similar fashion, this tells me how much y changes as x changes. And this tells me how much a changes as p changes. Okay? Now, the way we don't usually say it like this, though, in this class, instead of saying how much s changes as t changes, we say the derivative of s with respect to t, or the derivative of y with respect to x, or the derivative of a with respect to p. Okay? That's how we say it in calculus. But basically just telling you how much one variable changes as another variable changes. The one on the bottom is the input, or the independent variable. The one on the top is the output, or the dependent variable. All right, another thing we want to make sure that we're familiar with today is units. So you guys know how to do length. Length would include things like inches, centimeters, miles, right? Area, though, is always measured in square units. So, for instance, square inches, square centimeters, or square miles. Volume is always measured in cubic units. So that would be cubic inches, cubic centimeters, or cubic miles. Velocity. You guys know that's like a distance over time, right? So it could be any number of things, but it could be centimeters per second, or inches per hour, or whatever. Acceleration is the same thing as velocity, but the time factor is squared. Okay, so it could be centimeters per second squared, or inches per hour squared. And that's what we talked about in lesson 4.8. Okay, so I want to make sure that you understand concepts behind units there a little bit, because we'll be using those problems to do what we're working on in this lesson. All right, so to introduce the concept of what a related rate is, I want you guys to ponder something with me for a moment. Suppose you throw a pebble into a pond. What happens when you do that? Well, it creates concentric circles, right? It causes ripples that kind of go out and make concentric circles. Now I'm going to pull all these circles apart, okay? And what I'm going to do is I'm going to make a table of values that show us the time, radius, and area of each circle. So let's say after 1 second has gone by, the radius of the circle is 2 centimeters. And after 2 seconds have gone by, the radius is 4 centimeters. And after 3 seconds have gone by, the radius of the circle increases to 6 centimeters. And by the time we get to the 4th second, the radius of the circle is 8 centimeters. And then finally, by the time you get to the 5th second, it turns into 10 centimeters long. Okay? So as you guys can see, as time goes by, the radius is increasing, which is what we would expect if you were to throw a pebble into a pond. Now, in real life, I think the radius of these circles would be increasing at a much faster rate than that, but I'm just trying to keep the numbers simple for our purposes here. So we're looking at time values of 1, 2, 3, 4, and 5 seconds. And we're looking at, for 1 second it was 2, for 2 it was 4, and so on for the radius. Okay? Now, if I were to ask you guys how fast or how much is R changing as T changes? Okay, how much is R changing as T changes? Well, for instance, as I go from here to here, R increased by 2. And from here to here, T increased by 1. So, R changes by 2 as T increases by 1. And we make a fraction out of that. And that represents the derivative of R with respect to T. That's how much R is changing as T is changing on this interval. Now, same thing here. From here to here, that's 2, and that's 1. So the rate of change is constantly the same. We can see that the derivative of r with respect to t is always going to be 2. R increases by 2 centimeters for every 1 second that goes by. All right. But now I want to look at a new concept here. I want to introduce a new measurement into our story problem here. I want to talk about the area of these circles. Now, as you guys know, area of a circle is pi r squared. So, what would be the area of the first circle? Well, since the radius is 2, if you plug that in for r, 2 squared is 4, so you end up with 4 pi. What would the area of the second circle be? It has a radius of 4, so that would be 16 pi. And how about for 6? 8, and finally 10. Now, now I'm going to ask a new question. Say, how much is area changing over time? All right, so let's do the same thing we did before. From here to here, 16 pi, if you're going from 4 pi to 16 pi, then it increased by 12 pi. So the area increased by 12 pi. And that took 1 second. So the rate of change of A with respect to T is about 12 pi square centimeters. Remember, area is measured in square units. So the area increased by 12 pi square centimeters in 1 second. So the area is increasing by that many centimeters per second on the interval from 1 to 2. But let's go ahead and take a look at the next one. From circle 2 to circle 3, it increased by 20 pi. To get from 16 to 36, it goes up by 20 pi square centimeters per second. And from here to here, to get from 36 to 64, that would be 28, I believe. Yeah. 28 pi square centimeters per second. As you guys can see, as time goes on, the rate at which the area is increasing is increasing. What do we call it whenever a rate itself is increasing? That's acceleration, right? The rate is increasing. So that's an acceleration. That's a positive acceleration. That doesn't have anything to do with our lesson today, really. But I just wanted to pull in stuff from last class to kind of hope that makes some sense. But there it is. So we don't know exactly what the derivative of A with respect to t is at this point in time. But we do know that A is changing over time. But I could change this question, okay? Because A is not just changing over time. But you can see here from our formula, A is changing as R is changing, okay? So instead of saying what's the derivative of A with respect to t, you could also find how fast is A changing as R is changing. Now, you're still going to get some different values, but we could do the first one here. Let's do this one in green. So how fast is A changing as R is changing? Well, on the first interval, once again, we're going up by 12 pi square centimeters. How much is the radius going up by? 2 centimeters. Okay, so that would mean that the derivative of A with respect to R is 6 pi square centimeters per centimeter. Okay, and so what that means is for every centimeter that the radius increases, the area is increasing by 6 pi. Now, it'll be different if you were to go from here to here, because, as we said, the rate of change of the area is actually accelerating. But there we have it. Now, my point here is this, is that we have two rates in this problem. We have the rate of change of r, and we also have the rate of change of a. And those two areas are related to each other. I'm sorry, those two rates are related to each other. You guys can imagine that as r is increasing, that's going to cause area to increase. Therefore, the faster that radius increases, the faster area will increase. In other words, the rate of change of r with respect to t will determine the rate of change of a with respect to t. So these two rates are related to each other. And so today's lesson is what we call a related rate. Okay? All right, so what we'll be looking at today is first of all talking about what a related rate is and how can we solve them then. And so what are they? Related rates are two rates that are somehow mathematically related to one another. Kind of like we saw how the rate of change of the radius was related to the rate of change of the area of our concentric circles there. And what is a related rate problem? So these are the types of problems we'll be looking at today. A related rate problem is a problem containing two rates that are related, two related rates, in which we'll use one of the given rates to find out what the unknown rate is. Okay? Now, all these problems, I'm going to try to stick to these same 6 steps the whole way through. And they're pretty much, they're going to have the same steps every time. The only thing that will be different probably for each individual problem will be step 6, which is where you start plugging stuff in and solving. It may require a few algebraic moves and whatnot, but for the most part, these first 5 steps will be pretty much the same all the way through. All right. Now, before we get started, you're going to want to be aware of some basic formulas that will come in handy when you're doing related rate problems. You can make related rate problems about just about anything, okay? But I'm going to be focusing on problems that are pretty common to see when you're dealing with related rates. And those are things that pertain to area or circle areas, sphere volumes, cone volumes, right triangle geometry, which usually involves the Pythagorean theorem. And even sometimes every once in a while they'll throw in some angles of right triangles, which involves SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and so on. So those are the kinds of problems we'll be looking at over the next few days. Okay. All right, so let's take a look then at our very first problem. So let's read it first. A pebble is thrown into a calm pond and the ripples form concentric circles. If the radius of the circles are increasing at a rate of 2 feet per second, how fast is the area changing at the moment when the area is 25 pi square feet? All right, so tying it back to the very first example that we did today, but I'm going to show you how that looks with our process here. So the first thing we want to do is draw a circle, or draw a picture, okay? Now, sometimes these pictures are helpful and sometimes they're just kind of like a little extra work. In my opinion, for the first 2 problems we're going to look at today, the pictures are kind of unnecessary, but I'm just going to stick to my steps just because I want you guys to get used to the 6 steps I gave you. But we're talking about a circle here, and it has a radius. Now, that radius is changing. That radius is not constant. Now, when you draw a picture for step 1, anything that's changing, you want to put a letter there for it, okay? If it's changing, we're going to put a letter there. If it's a constant value, then we'll put a number there. But if it's a changing value, we're going to put a letter there, okay? So that's about it. That's all I can really draw for my picture. Number 2. Number 2, was to identify the given rate. I might be getting step 2 and 3 mixed up, but it doesn't really matter what order you do those two in. But step 2, let's say we want to identify the given rate. So we're looking for the rate that we know. Now, a rate is something that is like feet per second. And so right here is our given rate. So we have a rate of 2 feet per second. But what's important in this step is that you identify that this is a rate where you're taking the derivative of something with respect to something. And it's your job to figure out what those somethings are. Okay? So, what does this represent the derivative of? This represents the derivative or the rate of change of the radius. So I'm going to put an R right there. Since 2 feet per second represents how fast the radius is changing, I'm going to put an R there. Now just so you guys know, the bottom in these problems is almost always going to be t. It's time. But you could tell that from right here. It's seconds, so we know that that's time. Whatever's the denominator on the right side is what the units are for the denominator on the left side there. But on the top, feet isn't very clear sometimes. That feet could represent a lot of other things. So you kind of have to know that we're talking about the radius of the circle, which the problem tells you here. So you need to make sure that you write it out correctly. dr dt means how fast is the radius changing over time, and the answer to that is 2 feet per second. So you need to identify your given rate and make sure you label it appropriately. Step 3 is you want to identify the rate that you want to find. So in other words, what rate are they asking us to figure out? Well, let's read it some more. How fast is the area changing? That's a rate that we don't know because they're asking us how fast is it, so that means I don't know what it is. And what is that rate the rate of? It's the rate of change of the area. So we know that we're looking for how fast the area is changing over time. And so that would be dA dt, where A represents the area. Now, we don't know what the answer is at this point, but it might be good to go ahead and include our units now so we don't forget. So what are the units for area? Well, since we're doing feet, and this is area, it's going to be square feet, and T represents time, so it's seconds. So the rate of change of the area is going to be in square feet per second. And this is our goal. I want to know what is this number? How fast is that area changing? So let's review really quick. Step 1, draw a picture, put a letter for anything that's changing. Step 2, identify the rate that they give you and label it appropriately. And step 3, identify the rate you're trying to find, and you might want to include the units as you do that step. All right? Now step 4 is to identify a formula that will help us get our answer. So we're looking for a formula that will relate these rates together. In other words, I'm looking for a formula that will have an R and an A in it. Well, since we're talking about circles, what I would have you guys do at this point is go back to our formula sheet here. And do you guys see anything about circles on here? There it is. The area of a circle is A equals pi r squared. And does this formula have an A and an R in it? It does. So since we have a formula about circle area that relates the two variables I care about, R and A, that's the formula I'm going to use. So I'm going to use A equals pi r squared because now I have a formula that relates the two variables that I care about. But here's the thing. This formula only relates area to radius. But I don't want to find just what's the relationship between area and radius. I want to find what's the relationship of their rates. And so that's the purpose of step 5. Step 5 is going to take this formula that relates area and radius, and it's going to turn it into a formula that relates their rates. And the way you do that is by taking the derivative with respect to time. Okay, so I'm going to take the derivative with respect to t of this formula right here. Now, let's go ahead and do that. Take the derivative of a, you're just going to get 1 because it's just a variable. But notice since this doesn't match this, we have to put an a prime there, right? But instead of putting a prime, we're going to put dA dt. Next, let's find the derivative of this. How would you find the derivative of that? Well, you're going to take this 2, and you're going to multiply it to the front. And then you're going to take 1 away from that power, which leaves you with 1. But we don't really need to write the 1. But once again, since this variable doesn't match this variable, we need to put an r prime there, right? But we're not using our prime notation today. What am I going to write instead? dr dt. I don't really need this 1 here in the front either. But there you have it. So, after you find the formula that relates the two variables that you care about, you find the derivative of it. And that's implicit differentiation. So the derivative of a is dA dt, and the derivative of pi r squared is 2 pi r, because of the power rule, times dr dt. Okay? So, there is step 5. Now step 6 is to just start plugging in what you know and solve. And remember, what am I trying to solve for? I'm trying to figure out what is dA dt. I want to know what is that equal. So I don't know what this is. But that means I should know what the r is, and I should also know what this is. All right. So let's just start plugging some stuff in. Like I said, I don't know what dA dt is, so that's going to stay the same. And that's what I'm trying to solve for. I don't know my radius yet, but I will in a second. But I do know dr dt. Up here, we know that dr dt equals 2. So I'm going to replace this dr dt with 2. So right now what I need to find is I need to find my radius. What's my radius? Well, the radius is constantly changing. But what they're asking us to do is they're asking us to find how fast is the area changing when the area is 25 pi square feet. Okay, so since the radius is constantly changing, the area and its rate of change is also constantly changing. And so the rate of change of a with respect to t depends on what the radius is at any given point in time. And what point in time are we really worried about? I want to look at the point in time when the area is 25 pi. So if you have a circle whose area is 25 pi, what would the radius be at that point? Some of you guys could probably just do some mental math here and get it, and that's awesome, but you don't have to. You just solve for r. So basically you take your area formula, plug in the area you know, and you can solve for r. So if you divide both sides by pi, that goes away. And then if you take the square root on both sides, you get 5. Now technically you get plus and minus 5, but when you're doing geometry, we don't include negatives. So 5 is the answer. So I know that my radius at the moment when the area is 25 pi would have to be 5. So if I put all this together, I'm going to have my answer. That's going to end up being 20 pi. And remember the units? They were supposed to be square feet per second. And so at the moment when the area of this circle has reached 25 square feet, the rate of change of the area is 20 pi square feet per second. All right. So let's review the steps one more time. Step 1 is to draw a picture. Remember to put a letter for values that are changing. Step 2, identify your given rate and include the units and the proper label. Step 3, identify the rate that you want to find with the units. Find a formula that relates the variables that you care about, in this case A and R. Take the derivative of that formula so that you end up with a formula that relates the rates. Step 6, start plugging in everything you possibly can. You should be able to plug in something for everything except for the one thing that you're looking for. And sometimes that's tricky because in this case it was easy to identify what dRdt was. They just told us that. But we didn't know what R was right away. We had to dig for that ourselves up here. But you should be able to plug in something for everything except for the one thing you're looking for. That way you're able to solve it. So there's your 6 steps. Okay? Now, let's go ahead and do another one here. Let's do those same 6 steps. Step 1. A balloon in the shape of a sphere is deflating. If the radius is decreasing at a constant rate of 3 inches per minute, how fast is the volume decreasing when the radius is 2 inches? All right, so step 1, we draw a picture. Now, we're talking about a spherical balloon with a radius that is decreasing. So my picture actually, in 2 dimensions, looks exactly the same as the other one, but let's be aware we are talking about a sphere here and not a circle. Step 2, let's identify our given rate. The rate that they gave me is the rate of change of the radius. So the rate of change of the radius with respect to time is not 3 inches per minute, but it's actually negative 3 inches per minute. Why? Because it says decreasing. So you might want to make a little note there. If decreasing, then that means that it's a negative rate. Okay? So be careful whenever you identify your given rate. If they tell you that something is decreasing or something to that effect, that means that your rate will be a negative. And they won't tell you that here. You have to get that from the language that they're using. Okay? So there's my given rate. What is my rate that I'm looking for? What rate am I trying to find? Well, that would be how fast is the volume decreasing? So in other words, I want to know what is dV dt. And what is the units for volume? Well, since we're dealing with inches, volume will be cubic inches, and time will still be minutes. So I'm wondering what is the rate of change of the volume with respect to time. Now, if the balloon is decreasing, that means the radius is decreasing, which means that my rate will be negative, right? But if the radius is decreasing, I would expect the volume to be decreasing as well. That means when I'm all done, I should expect to see a negative number here. If I don't, something's wrong. But there's our first 3 steps. Let's move on to step 4. Now I want to find a formula that relates the 2 variables that I care about. I care about the radius and I care about the volume. So I'm looking for a formula about spheres that relates volume and radius. And our little worksheet has just such a formula. The formula that concerns the volume of spheres and radiuses looks like this. V is equal to 4 over 3 pi r cubed. So I've got a formula now concerning the volume of a sphere that relates the volume to its radius. Step 5, we're going to find the derivative of that formula with respect to t. All right, so if I take the derivative of v with respect to t, I end up with dv dt. If I take the derivative of this, we have to do our power rule, so I'm going to multiply the 3 to the 4/3. If you multiply 3 times 4/3, you're just going to be left with 4. and then you take 1 away from your power of 3, which will leave us with a power of 2. But don't forget to put a dr dt next to that, because this is implicit differentiation. So there is my new formula that relates the rate of change of the volume to the rate of change of the radius. Step 6, we're ready to just start plugging stuff in. Now, I know that I don't know what the volume is because that's what I'm trying to find, so this is going to stay the same. Okay? And just so you guys know, the one you're looking for will not always be on this side. Sometimes you could be looking for the one that's on this side. But the point is I don't know what dV dt is, so that's going to stay the same. Equals 4 times r squared times dr dt. Now, do I know what my r is, my radius? This time they actually tell us what the radius is. They tell me it's 2. Last time we had to figure it out ourselves. This time they just tell us. Do I know what dr dt is? We do. They tell us that as well. It's -3. So this one is actually a little bit less work than the last one. So dV dt is going to be equal to 4 times 4 times -3, which is -48. And we want to include our units, cubic inches per minute. And so what this answer means is it means that we have a balloon that's deflating, and at the moment when that radius of the balloon is 2 inches, the volume is decreasing at a rate of 48 cubic inches per minute at that point in time. Okay? And so there is our answer, 6 steps. So I want you guys try one of these. Go ahead and pause the video here and see if you guys can figure out the answer to this question. All right, so why don't we treat this more like a guided practice where you guys can do each step one thing at a time, if it's helpful to you. Otherwise, if you want to just fast forward this and get straight to the answer, you can. But here's what your picture would look like. It's actually the same thing as the other 2 pictures we've had. Step 2 is to identify what rate you're given. So if you haven't done that yet, pause the video and give it a try. And that would be the result. They gave us the rate of change of the area with respect to time, and it's 20 pi square inches per second, and it's decreasing, right? So we should have a negative in front of our area. Okay, go ahead and try step 3, which is where you identify what rate we're trying to find. Pause the video here, and when you unpause it, you'll see the solution. So as you guys can see, we're looking for how fast the radius is changing. So that means we're looking for dr dt, and the radius is measured in inches, and the time is in seconds. So have that. All right, go ahead and see if you could do step 4, which is to identify the proper formula. Pause the video here and see if you can figure out what formula you would use. So since we're talking about the area of a circle, and we want to relate area to radius, then we would be using the formula for the area of a circle. All right, let's go ahead and have you guys, this one's an important step, to find the derivative of that expression. So go ahead and pause the video and see if you guys can find the derivative. And this is what you would have got. And then step 6, I want you guys to go ahead and plug and solve. Plug in all the stuff you know, and your job is to figure out what is dr dt. So this is what it would look like if you plugged in your stuff. Your radius is 5, and your derivative of a with respect to t is -20 pi. And the thing that we don't know is dr dt. Like I said, the thing that you're trying to find may not always be all by itself on the other side. It doesn't matter where it's located, it just matters plug in the stuff you know and solve for what you don't. So at this point, if I wanted to solve this, I would multiply these and get 10 pi first. And then I would divide both sides by 10 pi. So if I divide the right side by 10 pi, that cancels the 10 pi out. And if I divide the left side by 10 pi, I'm left with -2. So dr dt will be -2, and we don't want to forget our units. It's inches per second. And so there's our final answer. Okay? And so hopefully you were able to solve your first related rate question. let's go ahead and move on to some more samples. And like I said, the steps are going to be the same for all of these. It's just I want to expose you to as many different types of questions as possible, because you guys know with word problems, sometimes things are a little bit convoluted and difficult to identify. So let's go ahead and take a look at another example. This is a very common question. This is probably one of the most common ones there is when it comes to related rate questions. And let's go ahead and see. It says a 25-foot ladder is leaning against the side of a wall. If the base of the ladder is being pulled away from the wall at a rate of 2 feet per minute, how fast is the top of the ladder moving down the wall at the instant when the bottom of the ladder is 24 feet away from the wall? A lot of words there. But basically what's happening is you have a wall. And you have a ladder leaning against that wall. Now what's happening is somebody's pulling the bottom of this ladder away from the wall. And as that happens, you know, it's going to gradually be changing its shape, right? It'll look more like that after it's been pulled away a little bit. And so as that's happening, we have a couple of values that are changing. We also have some values that are the same. But as you guys can see, basically what this ends up giving us is a triangle. Not just any triangle, a right triangle. Now something that never changes is the length of the ladder. No matter how much you pull that ladder away from the wall, the ladder is always going to be 25 feet. So anytime you have a value that's not changing on our picture, we're going to leave that as a constant. Okay? So I'm going to label the ladder length as 25. But what will be changing is how high the top of the ladder is up the wall, because the further we pull it away, the lower the height is going to go. So I'm going to label the height with an H. And we can see that the height is going to be decreasing over time. As we pull the bottom of the ladder away from the wall, the top of the ladder is going to be sliding down the wall. Something else that will be changing is how far away the base of the ladder is from the wall. B is going to be increasing over time, because as I pull that ladder's base away from the wall, the length of the base from the wall is going to be increasing. So we have a right triangle who always has the same hypotenuse, but the two legs are changing. The vertical leg is decreasing and the horizontal leg is increasing. Okay, and so there's our picture. All right. Now, what is the given rate? You guys might want to pause the video and see if you can do some of these steps before I do them. But the rate that's given is that it says that the base of the ladder is being pulled away from the wall at a rate of 2 feet per minute. So there's the rate that they're giving me. But what are my labels? Well, the bottom is still going to be time. Okay, there's nothing fancy there. But what goes up here next to this D? Well, we're talking about how fast the base of the ladder is being pulled away from the wall. What letter did I use on my picture to represent that? I chose to use the letter B. So I'm going to put B right here. So the rate of change of B with respect to T is 2 feet per minute. This person doesn't have much of a life. Apparently, they have nothing better to do with their time than to pull the bottom of a ladder away from a wall at a rate of 2 feet every minute. This person's bored. I think they need a job. But they gave us a great math question, so we're going to go with it. All right, so we have our picture. We have our given. Step 3 is we want to find, or we want to know what rate is it that we're trying to find. Well, it says here, how fast is the top of the ladder moving down the wall? That would be this letter, right? I want to know how fast is that changing. So that would be the rate of change of H with respect to T. Now, we don't know what that answer is. We would expect it to be negative though, right? Because it's decreasing. We would expect this one to be positive because it's increasing. The base of the ladder is increasing its distance, but the height of the ladder is decreasing. So we'd expect this one to be positive and this one to be negative, but We don't know the answer yet for dH dt, so we'll leave it. But what we do need to know, put down right now, is our units. So what are the units? Well, what would height be measured in? Well, height is like a length, right? And length is just going to be in feet. It's not like area or volume. It's just going to be feet. And once again, it's per second. So we have our picture, we have our given, we have what we're trying to find. Now, I want to find a way to relate the base of my right triangle to the height of my right triangle. Do I have a formula that will relate the base and height of a right triangle? Well, actually, there's two formulas. I don't know if I have them both on our little list of formulas, but I can think of two formulas that would relate the height and the base of a right triangle. Here's one. Don't write this, but just watch, because this one's actually wrong. But the area of a right triangle is 1/2 the base times the height. You could do that. But here's another formula, and this is the one we're actually going to use. This is, when it comes to right triangles, very often you can do Pythagorean's theorem, where you do one of the legs squared plus the other leg squared is equal to the hypotenuse squared. So how will you know which one is the right one to use? Well, here's how you know. This whole problem is about the length of the sides of this triangle. It doesn't say anything about area. So I wouldn't want to use area because the problem doesn't tell me anything at all about area. So I know that I'm not going to use this one. Now, once again, I don't think I put that formula on the worksheet, but it is possible. That can be done. But in this case, we wouldn't want to do that because this problem has nothing to do with area. So the formula I'm going to use for this one is Pythagorean's theorem. Now I have a formula that connects the two variables that I care about. H squared plus b squared equals 25 squared. Okay. We can simplify this a little bit. 25 squared is going to be 625. Might as well just do that because you can. All right. So now we're ready for the derivative step. So I want to find the derivative of that formula with respect to time. All right, so what's the derivative of h squared? Well, it's going to be 2h times dh dt. We take the derivative like normal, 2h, but we got to remember to put an h prime next to it, which in this case is dh dt. Plus, same thing here. I want to find the derivative of b squared with respect to time, so that would be 2b db dt. And then finally, I'm going to take the derivative of a constant, and as you guys know, the derivative of a constant is 0. In other words, the height of the ladder will not be changing over time. Okay, step 6 is where we're going to start plugging some stuff in. So, what do we know here? First of all, do I know the height of my ladder? Well, we're looking at the particular point in time when the base of the ladder is 24 feet away from the wall. So we're looking at a particular point in time when this is 24. Okay? But other than that, I don't see a height. So right now, I don't know that. So let me wait on that for a second. We'll come back to that. So we have 2. We don't know what h is yet, but we will. How about dh dt? Well, that's what I'm trying to find, so obviously I'm not going to know what that is right now. Next, 2 times b. I do know b. b is supposed to be 24, so that's nice. How about db dt? Yep, they tell us that right here. So that's nice. They gave us a few things, and then it all equals 0, right? So we have an issue. I want to solve dh dt, but I can't do that until I know what the height of this triangle is at this point. So very often, whenever you're doing these types of problems, if there's a part you don't know, we did it earlier in our very first example, what you're going to do is you're going to go back to your original formula, and you're going to find the missing piece that you want first. So I want to know what h is, so I can use my original formula to do that. Let me show you how to do that. So if you're ever missing a piece that you need to solve for the piece that you actually want to find, what you're going to do is you're going to go back to your original formula and you're going to plug in the parts you do know. I do know that B is supposed to be 24. And since B is 24, if we solve this, what would that be? Oh, I should be able to do that in my head, but shame on me. I don't want to risk it. I'm going to go ahead and use a calculator. Minus that. So I get 49. And if you take the square root, you get 7. So now I know that the height would have to be 7. So if the base is 24, then the height would have to be 7. And so now I know. So sometimes when you're on step 6, you're going to come across a situation where you don't know one of the parts and that you need in order to solve the part that you actually want to find. When that happens, usually what you're going to do is you're going to go back to your original formula and use that to find the missing piece. Sometimes it could be a little bit more complicated than that, and you might have to use an entirely different formula to find the missing piece. But in this case, this will be good enough. So now that we've got everything plugged in, we're ready to solve. So I've got 14 dH dt is equal to, putting all that together, I believe that would be 96. Sorry, it's not plus, it's not equal, it's plus. 96 equals 0. And what we'll do is we'll minus the 96 on both sides, which will leave me with that. And then I'll divide both sides by 14, which will give me this. And I'm going to go ahead and use my calculator to simplify that. 96 divided by 14. It's a pretty weird looking answer. I think I'll just write it as a reduced fraction, actually. Let me make some more writing space for myself here. So dH dt, if I reduce that fraction, is going to be negative 48/7. If you want to write it as a decimal, you can. I'm just going to leave it as a fraction. And that is in feet per second. And notice it's negative, and we expected that because as the ladder is being pulled away from the wall, the height would be decreasing. So the rate of change of the height over time is it's decreasing by negative 48/7 of a foot every second. Or actually, it's minutes, isn't it? Wasn't it minutes? It was minutes. Made a boo-boo there. My bad. Okay, so there you guys have it. So pretty similar. So we had two differences. We had the idea of dealing with right triangles and using Pythagorean's theorem. So that's one thing that was different. But the other thing is kind of like example 1. If in the process of plugging stuff in, if you find that you're missing more than you should be, usually you'll just go back to the original problem to find that other little missing piece so you can finish the problem up. All right, so let's go ahead and have you guys try. Now, this is a slightly different problem, but I promise it really is the same thing as the other one. It's a Pythagorean theorem. I think the trickiest part, in my opinion, of this problem is going to be asking you guys to draw the picture. So what I'm going to do is I'm going to ask you guys to just try to draw the picture for right now. See if you can get the picture accurately drawn. And then unpause the video, and then I will show you a good way to have drawn this picture. Okay, so here's my picture so far. We have car A traveling west and car B traveling north, and they're going to meet up at a common intersection, right? I put a compass rose up here for you guys if that's helpful. And then the question is asking us about how fast is the distance between these cars changing over time. And the distance between these cars is represented by this hypotenuse here. Okay. Now, I'm going to put the A up here to represent car A, and I'm going to put the B right here to represent car B. And I'm going to put D here to represent the distance between those two cars. Now, on this problem, all three of these values are constantly changing. A is decreasing, B is decreasing, and D is decreasing. And so we don't have any numbers on this one, so that is one difference. What rate are we given here? Now, before you do this one, I'm going to tell you that you actually are given two rates, and that can happen. They have given us two rates. So what two rates are given? I'm going to let you guys pause the video here, write that down, and see if you can actually completely solve this problem now. Right? And when you unpause the video, you'll see the final solution. So I've gone through step 5 so far. I ran out of board space, so I'll show you guys step 6 in a minute. But for now, your two given rates were the rate of change of A with respect to t, in other words, the speed of car A, which is negative 50. It's negative because this length is decreasing. Same thing with car B. dv dt is negative 60. We're looking for the rate of change of D with respect to time. How fast is the distance between those two cars changing over time? As they get closer and closer to the intersection, that D is decreasing. Okay. Next, we have our formula. A squared plus B squared equals D squared. And then we have its derivative. Okay, so plugging everything in, we're going to replace A with 0.3. We're going to replace dA dt with negative 50. We're going to replace B with 0.4, dB dt with negative 60. D we didn't know, and we're looking for dd dt. And so that one will stay like that. And for the piece that we don't know, we go back to the original formula and we plug in the A and B values that we know to solve for D. So in that case, for that little missing piece I was missing, it would be 0.5. Multiplying all this together, you get negative 30. Multiplying all this together, you get negative 48. Multiplying this, you get 1, so you can just get rid of it. And then negative 30 and negative 48 makes negative 78, and that would be in miles per hour. So the rate of change of the distance between the two cars would be negative 78 miles per hour. All right. Now that's the end of our lesson. However, I have a third example that I'm going to do for you guys here, just because you're going to see one like this maybe in your homework or something. So if you want to watch an additional example to help you with your homework, you're welcome to, and I'll go ahead and do that right now. And once again, the tricky part about this is just learning how to turn the words into a picture. So a softball player is running from second base to third base at 25 feet per second. That's really fast. Is that even possible? I don't know. But once again, I'm just picking numbers that are convenient. At what rate is the distance from the player to the home plate changing when the player is 10 feet away from third base? So, well, let's start with something simple. I want to draw a baseball diamond. Okay. Now, our player is running from second base to third base. That's going to be right here. He's running that way. His rate at which he's doing that is 25 feet per second. Now, the question is, at what rate is his distance from the home plate changing when he's 10 feet away from third? Okay, so that's pretty wild there. All right, so here's home. Now, if this guy is running, then he's going to be at different points along this. So basically, his distance at the beginning will look like this. And then as he starts to run, it'll look like this. And then his distance will be like that. And like that. So every moment he gets closer and closer to third base, his distance from third base is changing. And so what we have then is we have this little right triangle right here, okay? And it says, at what rate is the distance from the player to home changing when he's 10 feet away from third? So in other words, when this distance is 10, how fast is this distance changing? Okay? It tells us that the bases are also 60 feet apart. So all of the baseball diamonds' lengths are 60. So I know that this has to be 60. And then here we'll just put P for player. So the player's distance from third is constantly changing. The player's distance from home plate is constantly changing. But the distance from third to home is constant. That's always 60. So that's what my picture would look like. Now at this point, now that I've gotten my picture all drawn, I really don't care about any of this stuff because that has nothing to do with my problem. This is my question. Okay, so there we have it. So there's our picture. After that, the problem becomes pretty similar. So if you wanted to, if you guys want to get some more practice with this, you could pause the video and see if you could finish it now. But once again, I think the hardest part here was turning the words into a picture. But if you don't want to pause the video, you can just watch me go through it. I'm going to do it now. So here we go. Given. What rate was given? They tell me that the player's distance from third is, well, he's running at a rate of 25 feet per second, right? So that's going to be how fast P is changing over time. But this is kind of a tricky thing also. If he's running towards third, what's happening to P? Is it increasing or decreasing? It is decreasing because he's getting closer and closer to third. Okay. What rate am I trying to find? Well, they're asking me how fast, at what rate is the distance from the player to home changing. So that would be D. So I want to know what is the rate of change of D with respect to time. And I would also expect that to be in feet per second. And I would also expect it to end up being negative because it's also getting smaller. All right. Next, I would want to find the formula that relates P and D. And once again, we're just going to use Pythagorean's theorem. So Pythagorean's theorem would be P squared plus 60 squared equals D squared. And we can simplify that to be this. Okay. Next, we want to find the derivative. So the derivative of P squared with respect to time is going to be 2P dP dt. The derivative of 3600 is 0, so I just won't include that. And then the derivative of d squared is 2d dd dt. And now we're ready to plug and solve. So, do I know P? Do I know the player's distance away from third? Yes, they tell us that it's 10. So we have 2 times 10 dP dt. We know that also. That's negative 25. Do I know D? I don't know D yet. And I'm looking for d dt, so that's just going to stay like this. So once again, we have a missing piece. So what do we do when we have a missing piece? We go back to our original formula. We plug in the value that we know so we can solve for the one we don't. So I know that P is 10. And so that's going to be 3700 equals d squared, which means that d is equal to whatever the square root of 3700 is. I think I'm just going to write it as a decimal. Now, we haven't done a whole lot of this in our class, but when we do write decimals, I want to remind you guys that AP exam wants us to round to 3 places. So the square root of 3,700 is 60.828. Okay, and that's what I'm going to put right in here. All right. So what do we have? Negative 250 times 2 is negative 500. Multiplying 2 times that, I get 121.655. And then dividing both sides by 121.655, we can end up with our final answer. Oops, so I'll write it like this. And I get negative 4.12. And once again, that's going to be in feet per second. All right, so that concludes our lesson for the day, and we'll see you guys next time.